In this video I'm going to be talking about the electromagnetic spectrum and spectroscopy. So first off, I want to talk about the features of a wave. A wave has amplitude, it has a crest and it has a trough. But more importantly, I want to speak to you about the wavelength. Now, one cycle of a wave looks like this. It goes up, it goes down, and it reaches the same point. Now, the distance with which it takes to do that is called the wavelength. So that there is called the wavelength. And it does that over and over and over. It repeats itself. But all things being equal, different waves in a vacuum will differ in frequency and therefore in wavelength. And that's because the wavelength is inversely related to the frequency. A longer wavelength will have a lower frequency, a shorter wavelength will have a higher frequency. But all things being equal, in a vacuum, different waves will have different frequencies and therefore different wavelengths. So looking at the electromagnetic spectrum, we can actually see there's short wavelength waves and there is long wavelength light waves. The radio waves that must travel 20-30 kilometers, they have a very long wavelength. And short waves such as X-rays, they have a very short wavelength, high energy and high frequency, and they're used to travel through very, very dense mediums. But in terms of scientists and in terms of what we need to know, we will be looking at instruments such as UV-vis spectroscopy, which will use the UV spectrum and the visible light spectrum. We'll be looking at infrared spectroscopy that looks at light in the infrared spectrum. We'll be looking at radio waves, which deals with nuclear magnetic resonance, and we'll also be looking at atomic absorption spectroscopy and colorimetry that deal with the absorption of light in the visible spectrum. So with the different techniques, the spectroscopic techniques absorb radiation or emit radiation at different parts of the electromagnetic spectrum. For atomic absorption spectroscopy, it deals with the visible part of the spectrum. For UV visible spectroscopy, it deals with not only the visible spectrum but also the ultraviolet spectrum. Now for these two, they're very similar because they're actually measuring the absorption of light in either the visible or the ultraviolet part of the electromagnetic spectrum, and that's actually measuring the amount of energy absorbed by electrons as they move from a ground state or a lower energy level to a higher energy level. And what that can do is that can actually tell us about the concentration of an absorbing species or an absorbing component within a mixture of components. So we can actually have a sample mixture with different components in it, but we can actually measure the amount of a specific component by looking at its ability to absorb specific parts of the electromagnetic spectrum. For infrared spectroscopy, it obviously deals with the infrared radiation part of the spectrum, and it actually looks at the vibration, stretching and polarity of molecules. And that can actually tell us about specific bonds and functional groups within a molecule, because that's exactly what the different infrared radiation tells us. Different bonds exhibit different types of infrared radiation. For nuclear magnetic resonance, what happens is the protons and neutrons in the nucleus of the cell have a certain type of spin. And for odd number molecules such as hydrogen, which one H only has one proton in the nucleus, and so that's an odd number. And 13C or 13 carbon, it has 6 protons but 7 neutrons, and as a result there's an odd number of particles in the nucleus. and they have spin, and when there's an odd number of particles with spin, there's going to be one particle that shows a certain spin state. And we can actually use that information to tell us about the different types of bonding environments, not only for hydrogen but also for carbon. But that deals with the radio wave part of the electromagnetic spectrum. So here we have a question from the 2012 chemistry exam, and it asks you to state a spectroscopic technique. Now we could look at any of these ones listed here, and we could actually state, what part of the electromagnetic spectrum does this technique use? And then we could actually say, well, how does this part of the electromagnetic spectrum interact with matter? And what information does this spectroscopic technique provide? Well, we would, for each of these specific spectroscopic techniques, we would provide the part of the spectrum, we would talk about how it interacts, and then we would say, well, what information does this provide? So if I was to pick infrared spectroscopy, I know that it deals with the infrared part of the spectrum. And how does this part of the electromagnetic spectrum interact with matter? Well, changes in the vibration of, now hold on a minute, should be vibration. You could probably get away with just saying vibration, but you might say vibration, stretching, and polarity of bonds within a molecule tell us info about the bonds in the molecule. The second part of that question says, what information does this spectroscopic technique provide? I've actually answered both. Changes in the vibration, stretching and polarity of the bonds within a molecule. That's the first part of the question. And the second part is it tells us info about the bonds in the molecule, which means we can identify the functional groups. So I might actually write that, allowing So, in a general sense, for spectroscopy, it utilizes the absorption and emission of the electromagnetic radiation by atoms. So with absorption, low energy electrons sitting in the ground state absorb energy to move to a higher energy level or higher energy state. For emission, excited electrons that have already absorbed energy, they return to a lower energy state by emitting photons of light. In absorption, they absorb photons of light, and a photon is spelt like this, a photon of light. That's what happens. In absorption, a photon of light is absorbed. In emission, a photon of light is emitted. Now, there are different types of photons of light which make up the different wavelengths of radiation in the electromagnetic spectrum. We can actually see that in this diagram here. We have an electron here, and as it goes from a lower energy level to a higher energy level, it's absorbing a photon of light. And as it does that, it can go to the first excited level, it can go to the second excited level, or even the third excited level. And if an electron is already in the first excited level, it can actually go to the second excited level or straight to the third. As well as that, if an electron's in the second excited level, it can also go to the third. So you can see here there's actually 6 different ways an electron can absorb energy in the form of different photons of light. Likewise, light can be emitted from electrons as they're going down from a higher energy level or excited state to a lower energy level or excited state. And the same thing, so you can go from the third excited state to the second, as well as the third to the first, the third right down to the ground state, the second right down to the ground state, second to first, first to ground state, and you have your different ways that you can actually emit light. Now it's important to note that the different emissions of light here result in different wavelengths of light. So as for this one, it's going from the third energy state or the third energy level right down to the ground state. That's going to emit a different wavelength of light than, let's say, this photon of light here. It's going from the third energy level right down to the first, which isn't as much as the third down to the ground state, which will result in a different wavelength of light. Here we have the absorption spectra of different elements, and we can actually use this information to analyze whether a particular element is present as for atomic absorption spectroscopy, which we'll get onto in another video. So for sodium, it absorbs light in the orange part of the visible spectrum. Now, it absorbs light here and here. And so that means that there is 2 different ways that sodium, that one electron in the valence shell of a sodium atom, there's 2 different ways that it can actually absorb light. Now I don't know whether it's going from the ground state to the first energy level, or to the second, or to the third, or even from the first to the second, or from the first to the third. However, it is certainly 2 of any of these possible outcomes. It's certainly 2, because there is 2 different wavelengths of light that it absorbs light in. For hydrogen, it's got 4 different ways that it can absorb light. So of the different types of light absorption, here going from ground state to the first energy level, or ground state to the second or third, or from the first to the second, or from the first to the third, or from the second to the third, 4 of those are probably 4 of these different possibilities here result in the 4 different wavelengths of light. So for emission spectra, it's the opposite. Rather than absorbing light at a specific wavelength, there's emission of light at a specific wavelength. So for hydrogen, for instance, it emits light at this part of the electromagnetic spectrum, this part, and this part. And so what happens is the electrons have already absorbed the energy. They're in excited states already, and they're going downwards into lower energy states. So of the different possibilities, 4 of the 6 ones that I'm showing now are probably represented by the electron, that one electron in hydrogen, as it emits light. So it can emit light from the third down to the ground, second down to the ground, first down to the ground, or third to first, second to first, or third to second. 4 of those possibilities result in the 4 different wavelengths of light emission for hydrogen. For sodium, because it only absorbs 2 types of photons of light, it can only then emit those 2 photons of light. And so again, for the 6 possibilities here, 2 of those possibilities will be a result of that one electron for sodium being going from an excited state down to a lower energy state in two different ways. It might be from the third down to the ground state, or the second down to the ground state, or whatever. But basically, there's only two ways that one electron in sodium emits a photon of light to go from a more excited state down to a lower energy level state. Now, all of the spectroscopic techniques that we're going to talk about in the next few videos are based on the fact that the absorption of light is proportional to the concentration of the absorbing species or the absorbing component within the sample mixture, the mixture of components. And we can actually target specific components in sample mixtures.